No, sir.
Okay, hello everyone. Good afternoon, all of you. So we'll start with today's quote. Okay, it says, "Be thankful for what you are now and keep fighting for what you want to be tomorrow." Okay, whatever you are now, you have to be thankful for that. As I told many times, we are better than many people. At least that is enough to thank God for that. And what you want to be is in your hands. Okay, so you have to fight for it to become like that. And today is the birthday of Lewis Carroll. Have you heard about his name?
Mathematician.
Yeah, mathematician, and actually he's very famous for not mathematics. We don't know actually what mathematics he has found out because we don't come across his name in mathematics books. But he's. Have you heard about Alice in the Wonderland?
Yes, sir.
Yeah, he is the author of that book. It's a very, very, very famous book actually. Disney, those people have taken the movie. I think some 2, 3 versions are there. Alice in the Wonderland, and it's so famous book. Many times in many novels, many authors cite some quotes from Lewis Carroll, Alice in the Wonderland. And there is a sequel he has written, Looking Through the Glass. Okay, this that also is taken as a movie, and they are very famous. But he's also a mathematician. Charles Ludwig Dodgson, this is the actual name, and pen name Lewis Carroll, was an English logician, mathematician, photographer, novelist, and remembered for Alice's Adventures in Wonderland and its sequel, Looking Through the Glass. And after graduating from Christ Church College, Oxford in 1854, Dodgson remained there, lecturing on mathematics and writing treatises until 1881. As a mathematician, he was conservative. He was the author of a fair number of mathematics books. For instance, a syllabus of plain algebraical geometry. His mathematics book, Euclid and His Modern Rivals, is of the historical interest. As a logician, he was more interested in logic as a game than as an instrument for testing reason. Okay, so he's very, very famous actually. Okay, so today we discuss about the jet propulsion cycles, and before going to that, one or two small things which are left out, I will cover those things. And I was talking about the polytropic efficiency. And so when you talk about compressor, so we have seen that if this is not 1, this is not 2 dash, this is not. I want to get propulsive efficiency. Okay, relation between polytropic efficiency and isentropic efficiency. Okay, so eta C and eta PC. Okay, so this is isentropic efficiency, this is polytropic efficiency. I want to get some relation between these two. Okay, if I take the isentropic efficiency, eta C is equal to how it is defined?
T2 dash
T naught dash minus T naught 1 by T naught minus T naught. Okay, so if I take T naught 1 common, it will become T naught 2 dash by T naught 1 minus 1 by T naught 2 by T naught 1 minus 1. Okay, and naught 1 to naught 2 dash, this is isentropic process. So this can be written as the pressure ratio, compressor pressure ratio to the power of gamma minus 1 by gamma minus 1, right? But T naught 2 by T naught 1, this is polytropic process. So this is RC to the power of n minus 1 by n. But here n minus 1 by n, we have found that for compressor, it will be like this. Am I right? So instead of n minus 1 by n, I will write this. So gamma minus 1 by gamma eta is minus. So this is the way compressor efficiency, isentropic efficiency and polytropic efficiency are related. Okay, in the same way, for turbine, if I write like this, so turbine efficiency, isentropic efficiency is equal to T03 minus T04 by T03 minus T04 dash, right? So if I take T03 common, 1 minus T04 by T03 by 1 minus T04 dash by T03. So in the same way, so 1 minus T04 by T03 is 1 minus P04 by P03 to the power of gamma g minus 1 by gamma g, or inverse of the turbine ratio, because turbine pressure ratio is P03 by P04. So it is inverse of that. So I can write this as 1 by RT to the power of gamma g, n minus 1 by n by 1 minus, this is isentropic only, so RT to the power of gamma minus 1 by gamma. Again, if you see for the turbine, we have seen that n minus 1 by n is equal to eta pt into gamma minus 1 by gamma. Here it will multiply. So this I can write it as eta t is equal to 1 minus 1 by turbine pressure ratio to the power of eta pt into gamma minus 1 by gamma by 1 minus 1 by RT to the power of gamma minus 1 by gamma. Is it clear? So this is the way eta p and eta t, and there eta c and eta p polytropic efficiency I can relate. And if I draw a graph, because always graphs talk more, if I take r is on the x-axis and eta on the y-axis, if I take a case of eta p is equal to eta pc is equal to eta pt is equal to 0.85. I take a stage having 0.85 efficiency. Okay, suppose this is 0.85. So as pressure ratio increase, what happens to the turbine efficiency? Will it increase or decrease as number of stages increase?
Decreases.
Turbine efficiency.
Increases.
Increases.
Turbine efficiency increases because of
Reheat.
reheating effect, right? Reheating
Yeah.
effect. So it comes like this. Okay, so this is eta t. What about compressor efficiency?
Decreases.
Decreases. And it decreases more because nature always tries to trouble me only. Advantage will be less and disadvantage will be more. So it will be something like this. This is eta c. Okay, so like this, I will have the relation between polytropic efficiency, compressor efficiency, and turbine efficiency. Okay, this is one thing I wanted to talk. And there are some more efficiencies. This is for some theoretical interest. This is not that useful for the problems, but there are some more efficiencies, right? Suppose if I take compressor.
So what about isentropic efficiency?
Yeah. Eta C is isentropic efficiency. Eta T is isentropic efficiency of compressor and turbine. Eta PC and eta PT are polytropic efficiency of compressor and turbine.
Sir, isentropic efficiency is means it is already defined. It cannot change.
Yeah, it will change. Okay, polytropic efficiency is like stage efficiency because infinite stages are there. Okay, so each stage is having 0.85. If I have number of stages stacked together having 85% each, then compressor efficiency will reduce and turbine efficiency will increase. Though eta C and eta T are isentropic efficiencies, And polytropic efficiency is constant for all the stages. Am I clear about it? That is like stage efficiency. Polytropic efficiency is like stage efficiency.
Okay, sir.
Okay. So if I take compressor.
So, but in previous case, you have taken the polytropic efficiency variation.
No. That is wrong. I take polytropic number of stages each having a polytropic efficiency of 8.85. Okay, so as number of pressure ratio increase, number of stages will increase, and my compressor efficiency will decrease because of the preheating effect, and turbine efficiency increases because of the reheating effect.
Okay, sir.
Okay.
Yes, sir.
Eta T is constant, 0.85. I have taken that. So if I take 0.85 in the previous in this relation, right? So gamma is 1.4 and the eta PC 0.85. If I take for different of compressor pressure ratios, I can find out what is eta C.
Yes, sir.
Okay, so in that way, I am getting the relation between polytropic efficiency and isotropic efficiency as a function of pressure ratio.
Yes, sir.
Right. Okay, here, if I take static conditions 1, 2 dash 2. Okay, all static conditions if I take, and if I find out the isentropic efficiency of the compressor, this is called as static to static efficiency. Static to static, which is equal to T2 dash minus T1 by T2 minus T1. Previously, before discussing about stagnation conditions, this is the way we have found out, right? Now, if I want to find out the total conditions, how to get the total conditions? T naught is equal to T plus C square by 2Cp, right? Where C is the velocity. Okay, so T naught 1 is T1 plus, if I take this as C1 square by 2Cp, this will become naught 1. Is it clear?
Yes, sir.
Similarly, naught 2 can be obtained like this. Okay, there will not be much change. Okay, a little bit change will be there, but not very much. So C2 square by 2Cp, and this is naught 2. So if I want to draw the TS diagram for total conditions, it will be like this. This is naught 2 dash. So I will have total to total efficiency as T naught 2 dash minus T naught 1 by T naught 2 minus T naught. Is it right?
Yes, sir.
And if C1 is equal to C2, then total to total efficiency is equal to static efficiency. Okay, because here C1 C square by 2Cp added, here C square by 2Cp added, both get cancelled. Am I right?
Yes, sir.
Because T2 plus C square by 2Cp, T1 plus C square by 2Cp, both C square by 2Cp gets cancelled. So it will become like static temperature difference. So total to total efficiency will be equal to static efficiency. Okay, like this, we define two efficiencies like this. And coming to turbine, in the same way I draw. This is 3, this is 4 dash, this is 4. So I will have static to static efficiency as T3 minus T4 by T3 minus T4 dash. Similarly, if I add here C3 square by 2Cp. This will become 0.3. And here also I add this is C4 square by 2Cp. And this will become 0.4. Okay. And if I draw a line like this will become 0.4 dash. And T03 to T04 I will write. So if I draw like this, then total to total efficiency is T03 minus T04 by T03 minus T04 dash. Similarly, if C3 equal to C4, eta Tt is equal to eta Ss. But here, one more efficiency will be defined. This is called as total to static efficiency. Total to static efficiency, what I do is T03 minus T04 by T03 minus T4 dash, not T04 dash. I am getting T4 dash. Okay, there is some difference between this. This is the only particular one I wanted to explain. Okay, so the total to total efficiency and total to static efficiency. Okay, here the denominator.
So in static, T0 T minus T4 dash, how it is?
I'm telling this. This is the way it is defined. Total to static efficiency defined like this. Okay, total to total is defined. Static to static is defined like this. So why it is, I will tell you. Okay, the difference between this and this. Okay, why here T04 dash? And I am getting actual one is this one. Okay, this is actual work. And ideal work, how much I have to get? If it is total condition, this is the one. Okay, so if I am utilizing the kinetic energy at the exit of the turbine for some purpose, then I can use this. This is the ideal one. This is the actual one. I have to take the ratio. But suppose I am leaving it to the atmosphere. Okay, so then this is this velocity, kinetic energy is going to be a waste. Am I right or not?
Yes, sir.
It is going to the atmosphere. It is going to be a waste. So my efficiency should not be compared with only this. I have to compare with the total the one, right? My efficiency should be less than what I expect. So I have to take this. If this is used, if the kinetic energy of the last stage is not utilized and the gases are left into the atmosphere. Okay. Okay, then what is the case when I utilize this kinetic energy? If I have a jet engine, right, that will be expanded in a nozzle. Am I right? That energy is utilized in the nozzle. I get thrust. Suppose I have multi-stage turbines. The first stage turbine, it is the gases are going to the second stage, so that kinetic energy is not lost. The total condition is the total energy is going to the next stage. Am I clear? Am I clear about that?
Yes, sir.
So in jet engines or in an intermediate stage of a multi-stage turbine, kinetic energy is utilized. And in these cases, I have to use this total to total efficiency. So if it is not used, I have to get less efficiency, right? That's why the denominator will be more here. So total to total efficiency will be more than total to static efficiency. Am I clear? Am I clear about this concept?
Yes, sir.
Yeah. Okay, this is what just I wanted to cover before I go to the next chapter. So today we talk about jet propulsion. Okay, here again we will just see what are the advantages of gas turbines over IC engines. Okay, what are the advantages, main advantages? Can you tell me?
Higher efficiency.
Efficiency is not that high actually. Efficiency will be almost same.
High RPM due to which we can
High speeds. Okay, high speeds.
and
Why
stability.
high speeds? Why we can go for high speeds?
So because in rotational we can
Yeah,
we can
we
high
get
stability.
direct rotation. We get direct rotation of the shaft. But in IC engines, we get actually reciprocating motion from the engine that is to be converted to rotary motion. Rotary motion I need finally because shaft is to be rotated. Shaft power is needed. So I get directly shaft power. That's why there is no conversion of reciprocating to rotary. Reciprocating will be slower and there will be mechanical efficiency. It is to be during conversion. So all those losses will be there. So it can go for very high speeds. And
So power to weight ratio.
yeah, very, very important. Power to weight ratio. Very high. So this is one of the important thing which makes it useful for power generation or the aircrafts. Aircrafts, there is one more advantage. What is that? This is what is called as frontal area. And engine will have aerodynamic shape, due to which less drag. Am I clear? The cross-sectional area perpendicular to the flow direction, it will be small. Am I clear? So IC engine comes like this. If you see the aircraft engines, right, hanging below the wings of the aircraft, this type of shape you will see. Am I right?
Yes, sir.
So because of that, the cross-sectional area is very less for the given power. And if you have IC engines, right? Okay, first of all, okay, before later I will go to that. Okay, frontal area, that is, these are the main advantages. Okay, naturally other things will be there because of the direct rotary motion we get. So because of direct rotary motion, no balancing problem. Okay, high mechanical efficiency and very less noise and less vibrations. Okay, so all these things will come because of that, because of direct rotary motion. Is it clear? And so, as I told, one of the main disadvantages is part load efficiency is less. Okay, so because of this, if I don't need much variation in the speeds, this is very good option. Only for automobiles where I need to change the speed often, this is found to be disadvantageous. That's why it is not came into the application of automobiles. So as I told, still they use in sports cars, right? Because they run at almost constant speed, okay? And aircrafts, okay, constant. Most of the time, as I told, cruising speed, and even power plants. So all these things we can use, but not for automobiles. Is it clear? Okay, so coming to the gas turbines now. So I have two main applications. What are they? Power generation and aircraft propulsion. Okay, these are the two main applications. Okay, though we use gas turbines for this and this, the needs are different. The way of designing will be entirely different for power generation and aircraft propulsion. Why? Because in power generation, the important efficiency is important here. Efficiency is very important because the power is used by common man. Okay, so the unit cost should be unit cost of power should be less. This is very important, right? So this is the main goal. I want to have very cheaper power I need. But in aircrafts, the users are rich. Okay, so efficiency is of secondary importance. What is the primary importance?
Weight.
Power. Power is very important. Okay, next, weight. Because rich man need large power, right? They want speed and comfort, those things. And but aircrafts, we need the weight should be less. So high power should be there, less weight should be there. So power to weight ratio should be very high. And another thing I told, frontal area. Should be least. Here it doesn't matter. It can occupy any amount of space, right? So here weight and space, and frontal area all are important in the aircrafts. Am I right? So here in the land application, it can occupy any amount of area. It doesn't matter at all. Okay. So these are one of the main, though we design gas turbines only for both the application, the main attention will be different. The design way of designing is different for both the cases. So this is one thing I wanted to stress on. And also we have to see the effect of many things. In aircrafts, inlet conditions change, altitude change, okay, speeds change. So all these things are to be taken care of in aircraft applications. See, in power generation, I need not worry much about that. Okay, so initially, if you consider at the time of Wright brothers, okay, so how did the aircraft fly? How did they get the power? How did they get the power?
Sir, is it mechanical linkage, sir, by cycling?
What is that they have used to generate the power?
They kind of use a cycle Or
No. Wright brothers, did the cycle. Have you seen any movie or anything where Wright brothers have flown like that? Very large wings will be there, and it has to fly. No cycling, how it can fly?
So they just use
kind
the
of a
propulsion.
aerodynamic lift they have used, like paragliding races.
No, they used IC engines only. They used IC engine. Okay, but how do you get the power from IC engine? Thrust. They have used an IC engine. Okay, but how do you get the thrust? Will IC engine produce thrust?
No, sir.
So in that also the main requirement would be rotatory motion, right? So,
What is that?
so the main requirement would be the rotatory motion of the shaft, right? So in that also,
Why do you want rotary motion?
so that the rotors can move at high speed.
Rotates?
Yes, sir, at high speed. The
No.
rotors can move.
How do you
Rotors
get the
can.
thrust? How do you get the thrust? It has to move forward, right? How do you?
Using propeller, sir.
Yes.
Propeller.
Yeah, right. IC engine rotates propeller. Okay. Propeller gives the thrust. The rate of change of momentum. So that gives the thrust. So some air enters and comes out. Propeller is a sort of compressor. Okay, it compresses air. Okay, so the pressure ratios are very, very small compared to fan also, right? But large mass flows.
Can
So
we say some propeller as a rotor?
yeah, propeller is a rotor only.
Yes, yes. Okay.
Propeller is a rotor only. Just you can see the propeller which is running before the aircraft engine, right? So that is the propeller. It's like a fan. Am I right or not?
Yes, sir.
So you look like a fan. It's open, right? Open turbo machine. So which rises the pressure, and so there will be change in momentum. So mass flow into change in velocity will give the thrust. This is called propeller thrust. So this is Newton's second law only. Okay, so it gives thrust. And so because of propeller rotates, right, it is sometimes this is called a screw propeller. Okay, if propeller rotates, why it moves forward? Just if you imagine, okay, a table is there. Okay, I take a screw and I rotate it. What happens when I am rotating it? On the table, I put a screw, right? I made a small hole maybe, and I put the screw in that. I turned it by screwdriver. So what happens? It moves forward, right? Is the connection there? People are there?
Yes,
Yes,
sir.
sir.
Yes, sir.
So it moves forward, right? In the same, that is on a stable table. If I rotate the screw, it is moving forward or backward, right? In the same way, if you take air is stationary, okay? So air is like stable thing. It's not moving at all, okay? A stationary air, if it is there, if the propeller rotates, it works like a screw. So it moves forward. Am I clear?
Yes, sir.
So it is that way. It's called as a screw propeller. Okay, so the engine is called as piston propeller engines. So initial engines are run by IC engines only. Even now, the small aircraft, some pilot aircraft, some trainer aircrafts, all those run by IC engines only, and they use piston propeller system. Okay, and So they run at very low speed. And if I want to run at higher speeds, so what should I do? I should have multi-cylinder engines, right? But it occupies a lot of space. At the time, space is very, very important. Okay, weight also is important. Okay, if I can suppose get some more thrust and lift, so I can go for multi-cylinder engines. But for the for that, what the people used is they used what are called as radial engines. Have you heard about radial engines?
Yes, sir.
So actually, all cylinders will be radially arranged like this. There will be only one crankshaft. Okay, and we get rotatory motion, and this is like this, arranged in a cylinder, radial fashion, so that the space occupied will be somewhat less, but still the weight is high. That's why I can go up to some 0.3 Mach or something like that. Less than 0.4. So it can go only up to that. Beyond that, it cannot go. And so they tried and tried, so they could not go for still higher speeds. Initially, people thought they cannot fly at all before Wright brothers. Even Wright brothers also, they had a doubt whether they can do it or not. But because of their persistence and determination and all, they tried and tried, and finally they could get it. So one of the main thing why they could not fly is because they depended on the data developed by the previous generation. That is the pressure distribution, velocity distribution, the lift, drag forces, and all those things. Because at the time, the instrumentation is not developed much, so the data that they got are not that reliable. So that's why what they have done is actually one of the brother, he told we cannot fly, it's unnecessary waste, and he lost all the hope. But the other fellow told, what we do is we develop our own wind tunnel, we develop our own data. So they constructed a small wind tunnel in their workshop, and they started doing experiments, and with their own data developed, they could fly within 1 year. Okay, so that's the thing they could do. Okay. So initially, they were only gas turbines are not yet developed, and as I told, it took a lot of time for the gas turbines to develop because the component efficiencies are less, and so whatever power initially it didn't move at all. Though conceptually they thought it will run, it didn't move at all. And after few years, it started rotating but not producing any power. All the turbine power is taken by compressor power. So it took many years of development. So as the component efficiencies of compressor and turbine gradually increased, they could get the net power. Okay, so once the gas turbines came into picture, the IC engines became outdated. Okay, so for small power, as I told, for trainer aircraft, pilot aircraft, or something like that, small things. Okay, so still they use the IC engines, but once the gas turbines came, when you want to have higher speeds, so this is gone. So then what we got is turboprop. So still there is a propeller, but this propeller is rotated by a turbine, which is directly rotating thing. So I can have very high speeds. So because of that, turboprop, how you get it? So like this, and so here I have compressor. I have turbines. I have combustion chambers here. And here there is a small gearbox. I have a big propeller here. and this is nozzle. Okay, so turbine runs both compressor and propeller. Because compressor speeds and turbine speeds are high, and propeller, because of the large diameter, it cannot run at very high speeds. So it will run at a bit lower speed. Because of that, I have gearbox. Okay, so combustion chamber and turbine, and after turbine also, if there is some more energy is there, that energy can be utilized in getting the expansion in the nozzle. So I get thrust. This is nozzle thrust, and here I will get propeller thrust. So the total thrust F total or F is equal to propeller thrust plus nozzle thrust. Okay, so this is the total thrust. Okay, the nozzle thrust is very small, propeller thrust is very high. So like this. Okay, this is the way they could go for high speeds, and they can go the Mach numbers up to 0.7. They can go for the Mach numbers up to 0.7. So here, actually, the mass flow is very high. So air enters like this. Okay, so much of mass flow comes, and some of the mass gets compressed here, and because of this mass flow, I get the propeller thrust, and some goes through the core of the engine, and due to which we get the nozzle thrust. Okay, so this a velocity that is coming is CA, and here this velocity is CJ. This is aircraft velocity. This is jet velocity. So the velocity of air entering the aircraft is equal to the velocity of the aircraft, isn't it? Assuming actually air is still and the aircraft is moving with CA. Okay, and so if I assume aircraft is still, so air is moving in with CA. Am I clear about it?
Yes, sir.
Yeah, like this. Okay, and so before going further, I want to develop some relations. Shall I do now? Okay, I will do it later. Okay, so mass flow is entering as m dot A with CA velocity and at pressure PA. And this mass flow leaving, actually here there will be m dot F will be entering here, and the mass flow leaving will be m dot A plus m dot F at CJ velocity. Okay, so this is the way it is going. So the mass flow is very high, and jet velocity is low, because most of the thrust is got obtained by propeller itself, and only a small thrust will be there with the nozzle. Okay, here up to 0.7 we got it, but why it is not going for higher velocities, still higher velocities? So why? Because if I take this, if CA is this, and the propeller is rotating, okay, so this is what is called as blade velocity. And so the relative velocity at which it is entering the blade will be higher. Okay, so if somebody throws a ball at you, and if you are running that side, so the ball hits at higher velocity. Am I right or not? If somebody hits you with a ball, okay, you will get hurt. But if you are running towards it with a higher speed, the relative velocity will be very high. Okay, so in the same way, CA, suppose this is some 0.6 Mach number, but because the blade is rotating, so C is equal to V plus U. V is called as the relative velocity, and U is the blade velocity, and c is absolute velocity. Okay, and the blade velocity, because it is rotating, it is tangential, and this is axial direction. Tangential direction will be like this. Okay, and so here c is equal to v plus u. So this will be v, this will be u, and v plus u equal to c. Am I clear? This is vectorial addition. This is not algebraic addition. This is vectorial addition. So if CA equal Mach number is 0.6, so what happens to relative velocity? Relative velocity will be more than that, and it may cross may become m greater than 1. Is it clear? Because the propeller is very large diameter, right? The blade speeds will be very high, pi dn by 60, u equal to, this is diameter of propeller. Okay, so at the tips, the speed will be very high. So the relative velocity at this tip may become more than Mach number 1, and there may be a shock. If there is a shock, what happens is, because of the sudden change in the pressure, the propeller used to get broken off and it used to fly and hurt, okay, many people. So it became very dangerous to go beyond some 0.6 or 0.7 Mach number. So up to Mach number 0.7, so they could run, but beyond it, okay, so Mach number with respect to relative velocity is greater than 1, and shocks occur, blades break, right? Like this it is happen. Is it clear?
Yes, sir.
Okay, so now they try to have something change in the design. Okay, so instead of leaving propeller like this, they ducted it in this way. They enclosed it. Okay, by enclosing it, what happens? Because the velocity which is coming is 0.8, 0.7, I want to reduce those velocities before it reaching the propeller. So what should I do? I have to use a diffuser before the propeller. So if I have like this, okay, so I will go to next page, and so here, instead of propeller, I have what is called as turbofan. Here it is ducted like this. So air enters at this point. Air enters at this point, and here I have diffuser, or this is also called as intake or intake diffuser. So what happens, by the time the air reaches the fan, the velocities get reduced. Am I clear? Here it is m equal to 0.7 only, but here m equal to some 0.3. There will not be any problem. So I will have again the same things: compressor, turbine, and nozzle, combustion chamber, like this. But here I have fan, and this is called as turbofan engine or ducted fan engine, because it is ducted, right? In this way I have. And here what happens is, there will be some jet coming like this. This is called as cold jet. This is also a nozzle only, okay, because it is a duct. This is like nozzle, this is cold nozzle, this is hot nozzle. Okay, so I will get what is called as cold thrust. Here, what is called as hot thrust, and the total thrust is equal to cold thrust plus hot thrust. Is it clear?
Yes, sir.
Okay, so here, if this is mass flow cold air, this is hot air, the total m dot is like this. Okay, so here this is also called as bypass engine, ducted fan or bypass engine or turbofan engine, because some of the air bypasses the main engine. That is, it is not going, like bypass road will be there, isn't it? So it will, without going through the city, it bypasses. In the same way, without going through the engine, it bypasses. So the cold air is also called as bypass air. Okay, so here we define what is called as bypass ratio. B is equal to m dot C by m dot H. Am I clear? And because of this, the Mach numbers can be up to 0.85. They have increased the Mach number up to 0.85. All the present passenger aircrafts use turbofan engines. Okay, if you see all old movies, all are turboprops only. You rarely see any other thing. Always you will see a propeller. But present day, if you see the aircrafts, you will not see some fan will be rotating, you will see, but it will not be projecting outside the engine and rotating like a propeller. Am I clear?
Yes, sir.
Yes, sir.
Okay, you people sometimes respond. Otherwise, I don't know whether you are there or the connection is cut or something like that. Okay, so because of that, the passenger aircrafts, all the present passenger aircrafts, all big aircrafts and all use turbofans only, and the Mach number it can go up to 0.85. Okay, and so as the actually 0.7 to 0.85, as the Mach number increase. Okay, so I want more thrust. So more thrust, how can I get? By reducing as F increase, m dot C decrease and m dot H increase. Because I want to put more fuel and more thrust, I can change this. I can increase the hot thrust. Okay, so cold thrust I reduce and gradually I increase the hot thrust. Am I clear?
Yes, sir.
So if I want to decrease the cold thrust, bypass ratio decrease. M dot C gradually decrease. And once it approaches 0.85, almost B equal to 0, M dot C equal to 0, I don't need any fan. Okay, we come to what is called as turbojet. So here I will have diffuser. And here I have compressor, turbine, combustion chambers, that side and this side, and nozzle. That's all. Okay, this is turbojet. Okay, because the here, okay, one more thing. Why the fan need is gone. Okay, here as in the diffuser, there will be increase in the pressure, right? That is called as fan pressure. Right? The fan pressure increases as the Mach number increase. Sorry, diffuser pressure, sorry. Intake pressure. that is in the diffuser, the in better way, pressure rise in diffuser increases with Mach number. Am I right? This is what is called as ram pressure. Ramming, you know, right? It rams because it is going very fast, the air rams into that. Okay, so that increases the pressure. This is called as ram pressure. So the pressure rises so much that I don't need any fan because the fan pressure ratio is very small, right? I don't need fan. Diffuser will take care of because of high velocities. The kinetic energy is converted to pressure energy in the diffuser, right? So that is so high, I don't need any fan. Am I clear now? So I will have intake diffuser, compressor, turbine, combustion chamber, and nozzle. This is turbojet. So the Mach numbers 0.85 to even 2 to 3. Okay, maybe up to 3 I can go Mach numbers.
Sir, actually the fan uses to produce the thrust, right, sir?
The cold thrust is reduced, no? Because hot thrust is increased, cold thrust is reduced, and finally the thrust due to cold jet is gone.
Okay, sir. But at the start, as the turbine is not working, then how could it start without any thrust?
Okay. You have to ask that question at the beginning only. How turboprop starts?
Maybe by
How
electric engine,
an IC engine starts?
by batteries.
Yeah, something like that. So initially I have to give a thrust. Okay, give a rotation with batteries. Here also we do that. Gas turbine, how initially it runs? By battery only. So
Sir, but for aircraft, it will be huge amount of.
yeah, but just very few seconds only I need. So once it starts rotating, the combustion chamber, because the burning takes place, only few seconds. It is like initial thrust you have to give, like kick.
So, sir, the takeoff before the takeoff, it runs with the like, we have to
Just at the beginning of the starting of the engine, I start it with starter motor only.
Okay, sir.
And how do you get the combustion? That's one question some people have to ask. How do you get the combustion here? We use spark plug. Okay, just like petrol engine, I use spark plug. But their spark plug is to be given spark throughout the running, right? Here it is not like that. For few seconds, I have to give the spark for starting of combustion. And once the temperatures inside is high, automatically it continues burning. It is steady flow machine, right? Is it clear?
Yes, sir.
Okay, so that is one thing. Okay, so now this is the turbojet, which can go from 0.85 to 3 Mach number. So mainly they are used in warplanes. Okay, passenger aircrafts will not go with such high speeds, right? So that's why we use it in warplanes usually. Okay. So here there is no propeller thrust or fan thrust or cold thrust. So there is only one thrust, one nozzle thrust. It's not only nozzle thrust. Actually, then we call this later. I will tell you. There are two thrusts. One is called as momentum thrust. Another is jet thrust, pressure thrust. Momentum thrust. This is pressure thrust. I will tell you later what they are. Okay. So this is the way turbojet works. And here, as the Mach numbers reach 2, 3 like that, so the ram pressure, as Mach number increase, ram pressure increase further and further. As ram pressure increase at Mach number 3, need of compressor, there is no need of compressor. No need of compressor. If you don't need compressor, do you need turbine? Turbine purpose is just to run the compressor. Is it clear?
Yes.
So no need of compressor and turbine. That is gone. We will have what is called as ramjet. Okay, what is there in ramjet then? There are only 3 things. Intake nozzle, intake diffuser, combustion chamber, and exhaust nozzle. Okay, this is ramjet. That's all. It's a duct. That's why it is sometimes called as athodide. Means aerothermodynamic duct. No moving parts. Very light. Very aerodynamic. Very high power to weight ratio. Okay. And Mach numbers, some 3 to 6. It can go up to Mach number 3 to 6. Okay, any questions now here? Here I will draw it some better way.
And
Okay, somebody is asking something.
sir, if there are no moving parts, how to reach up to 3 Mach number?
It can go up to 6 Mach number. Okay, so the question is, yeah, how can it start first?
Yes, sir.
How to get the ram pressure? Because of ram pressure, I am not, I have eliminated compressor. Well, ram pressure I will get only if it is running at high Mach number. But how can it go to high Mach number initially? So it is not
Self-starting.
It's not self-starting engine. It cannot start by itself. So somebody has to push it initially. And I can have maybe a small rocket engine. Okay, so which is fired up to some distance and then it goes off. Its fuel goes off. Or you can even leave it also. So some initial thrust I have to get, or I should have a launcher. Okay, I can have it like this. I should have a launcher which pushes it first at that high speed. So because of that, mainly they are used in missiles. So you know that missiles are launched, right? They go with very high speed. So this is convergent, divergent diffuser. How do you get the velocities supersonic to subsonic? I should have convergent, divergent diffuser. In the same way, this is Mach number less than 1, Mach number far greater than 1, Mach number far greater than 1. So this is again subsonic to supersonic, convergent, divergent nozzle. Is it clear?
Yes, sir.
Okay, this is the ramjet. So if I just like to compare, okay, I will write here. This is very important. Piston propeller initially, then we have got turboprop, Then we have got turbofan. Then we have got turbojet. Then we have got ramjet. And another thing also, there is what is called as scramjet. Okay, what is the scramjet? Have you heard about it? Have you heard about it? This is supersonic combustion.
Combustion ramjet.
Ramjet. Okay. So in ramjet or any other jet, all other engines, combustion occurs at subsonic velocities. It is very difficult to have combustion during supersonic velocities. If, air is very fast, so it cannot sustain the fuel, the flame. Am I clear? So I should have some special design for combustion at supersonic velocities. So scramjets, they are still in research stage only, not completely developed. And if they can have scramjet, I can have Mach numbers 6 to 12 Mach numbers. Okay. So these are scramjets. Okay, as I told, they are not yet completely into application. They are at research stage. So I write scramjet also here. So as I go down, so I can say the power to weight ratio. Power to weight ratio increase or decrease as I come down?
Increase.
Increases.
It increases like this. Okay. And the flight speed
Increases.
increase. And if you see mass flow of air, initially it takes a lot of air in the propeller. Later, when you have fan, it is reduced. Jet, it is reduced. The mass of air increases in the other fashion. Am I clear? And jet velocity increases down. And the efficiency, okay, before going to efficiency, so I go to fuel consumption, specific fuel consumption. So because I need a lot of thrust, I have to spend a lot of fuel. Okay, so SFC increases this way. And because of that, the efficiency decreases actually, it goes this way. Piston propeller, turbo propeller will have high efficiency. As I told, we don't bother about efficiency, we need thrust, speed. Okay, that's why we are going down. Okay, but if I want efficiency, turboprop is higher efficiency. And okay, aircraft speed and altitude at which it flies, it increases down, because as I go down, mass flow needed is reduced. At higher altitudes, I cannot have large mass flows. Turboprop will not work there. It need large mass flow. But turbojet, ramjet, they need less mass flow. So it doesn't matter. It can go at high altitudes. Am I clear?
Yes, sir.
Yeah. And frontal area. Frontal area reduce, right? Increases upwards. They become slim and slim. Okay, they become smaller engines. Like that. So individually power increase and weight decrease. Okay, individually power increases and weight decreases. So power to weight ratio increases more. And so space occupied or compactness. Okay, it become more compact. space occupied gets reduced. Okay, it's I don't know how I. Okay, compact I will tell you, or volume occupied. I think it give a wrong meaning. Okay, so what should I do? It should decrease actually, so I have to give other way. So volume or space, it increases upwards. Okay. Anything else? I think, okay, these are the things you remember relatively what happens. So SFC increase down, mass flow of fuel increases down.
Temperatures.
Yeah. These are the things you remember. So I think we'll stop here. So later, how to calculate the performance and how to do the cycle calculations and all, we will do in the next class. Any questions till now? Okay, the way I have presented actually the evolution of the aircraft engines, you will not get any textbooks, right? So you have to depend on my lecture only. You listen to one or twice or thrice so that everything will be clear to you. So in this particular fashion, you will not see in any books.
Sir, after turbojet, we don't need any compressor and turbines. So
Yeah.
do we need any combustor, sir?
Yeah, otherwise, where is the power?
Sir, what is volume space?
See, I have to increase the enthalpy so that I will have more kinetic energy I will get outside. So otherwise, whatever air speed it enters, it leaves at the same speed. I will not have any thrust. If I don't have any losses, no friction, nothing, then the air enters and leaves at the same velocity. It will not have the thrust. So the thrust is equal to m dot A into Cj minus Ca. So how do I get the increase in the velocity in the jet? I should put more energy into it. And how the energy is put into that? By increasing the M, because here enthalpy and kinetic energy, enthalpy is converted to kinetic energy. So delta Q is equal to dH plus delta W in the nozzle. Sorry. D of Ke plus delta W. In the nozzle, delta Q is 0, delta W is 0. So dH is equal to, or D of Ke is equal to minus dH. So enthalpy has to be reduced. So the more change in the enthalpy, the more kinetic energy I will get. And how to get large enthalpy? By burning more fuel in the combustion chamber.
Okay, sir.
Okay, combustion chamber should be there. So the ramjet actually it is a very simple one. It is like a combustion chamber with the nozzle and diffuser at the entry and exit. Okay, so no moving parts, absolutely.
Okay, sir.
Yeah. Any other questions? Okay.
Sir, what was volume space?
The space occupied by the
Engine. Okay, sir.
okay, so it becomes small and small, compact as I go down.
Okay, sir.
Yeah. Shall we go for the story?
Yes, sir.
Okay. And so here actually I retell a story which you already know. This is hare and tortoise story. So what is the, you know, hare and tortoise story, right? They go for a running race and hare goes fast and sleeps at the end, and then tortoise wins it, right? What is the moral of the story you learned from that?
Slow and steady wins the race.
Yeah, slow and steady wins the race. But now we know that if you're so slow and steady, you will be there only, right? So by believing that slow and steady wins the race, and if you are slow and steady, you will never win the race. We know that, right? So according to our times, it is to be changed. Okay. So how it is changed? I will tell you. It's a very interesting management lesson. Okay, once upon a time, a tortoise and a hare had an argument about who was faster. And so hare says, I am the faster runner. And it says, that's not true. The faster runner is me. And they decided to settle the argument with a race. They agreed on a route and started off the race. Okay, so, okay, let's have the race. And it said, fine. And the hare shot ahead and ran briskly for some time. Then, seeing that he was far ahead of the tortoise, he thought he would sit under a tree for some time and relax before continuing the race. And poor guy, even if I take a nap, he could not catch up with me, he thought. And he sat under the tree and soon fell asleep. And the tortoise, plodding on, overtook him and soon finished the race, emerging as the undisputed champ. And the hare woke up and realized that he had lost the race. And the moral of the story, slow and steady wins the race. And this is the version of the story that we have all grown up with. And the story continues now. The hare was disappointed and it started thinking, why did he lose the race? Okay, at losing the race, and he did some soul searching. He realized that he had lost the race only because he has been overconfident, careless, and lax. If he had not taken things for granted, there is no way the tortoise could have beaten him. So he challenged the tortoise to another race. Can we have another race? And tortoise is now overconfident. It said, okay. And this time the hare went all out and ran without stopping from start to finish. And he won by several miles. Okay, tortoise is very far away and it already won the race. And the moral of the story, fast and consistent will always beat the slow and steady. If you have two people in your organization, one slow, methodical, and reliable, and the other fast and still reliable as what he does, the fast and reliable chop will consistently climb the organizational ladder faster than the slow, methodical chop. Okay, this you can observe at any place, and your logic also says it's right. Okay, but it's good to be slow and steady, but it's better to be fast and reliable. But the story doesn't end here. Okay, so it continues. The tortoise did some thinking now this time. Okay, and realized that there is no way he can beat the hare in a race the way it was currently formatted. In this type of format, it understood that it can never win. And how can he win the race? So whenever if you are competing with another person, you have to check what are your strengths and weaknesses, other strengths and weaknesses. And if somebody is more strong in a particular aspect, there is no point in competing in that aspect. Okay, now what he thought for a while and then challenged the hare to another race, but on a slightly different route. And the hare agreed for sure. Okay, and he told, okay, can we have another race? This time we will go through the different route. And they started off in keeping with his self-made commitment to be consistently fast. The hare took off and ran at top speed until he came to a broad river. Okay, on the road, there is a river also. And the finishing line was a couple of kilometers on the other side of the river. Goal is there. So the hare sat there wondering what to do. In the meantime, the tortoise trundled along, got into the river, swam to the opposite bank, and continued walking and finished the race. And the moral of the story, first identify your core competency and then change the playing field to suit your core competency. You find your strengths. And in an organization, if you are a good speaker, make sure you create opportunities to give presentations that enable the senior management to notice you. And if your strength is analysis, make sure you do some sort of research, make a report and send it to the upstairs. And working to your strengths will not only get you noticed, but will also create opportunities for your growth and advancement. And this story still hasn't ended. The hare and the tortoise by this time had become pretty good friends, and they did some thinking together. Both realized that the last race could have been run much better. So they decided to do their last race again, but to run as a team this time. Okay, so the hare told, "Hi, buddy, how about doing our last race again?" And it told, "Great, I think we could do it much better if we two help each other." And they started off, and this time the hare carried the tortoise till the river bank. And there, the tortoise took over and swam across with the hare on his back. And the opposite bank, the hare again carried the tortoise, and they reached the finish line together. And they both felt a greater sense of satisfaction that they would felt earlier. Both of them came at the same time at the very, very less time. So it's good to be individually brilliant and to have strong core competencies, but unless you are able to work in a team and harness each other's core competencies, you will always perform below par, because there will always be situations at which you will do poorly and someone else does well. Teamwork is mainly about situational leadership, letting the person with the relevant core competency for a situation take leadership. So when you do a project together, so sometimes some strength is needed, sometimes some strength is needed. So if you can understand your competencies, so you can do this work, I will do this work better, like that. So there are more lessons to be learned from this story. Note that neither the hare nor the tortoise gave up after failures. That is one lesson. The hare decided to work harder and put in more effort after his failure. The tortoise changed his strategy because he was already working as hard as he could. So in life, when faced with failures, sometimes it is appropriate to work harder and put in more effort, or sometimes it is appropriate to change strategy and try something different. And sometimes it is appropriate to do both. The hare and the tortoise also learned another vital lesson. When we stop competing against a rival and instead start competing against the situation, we perform far better. That is more important. Rival is not another person, but you have to fight with the situation, not with the people. I think we are coming to the end, but beautiful story. Okay, so a very small story. When Roberto Goizueta took over as CEO of Coca-Cola in 1980s, he was faced with intense competition from Pepsi that was eating into Coke's growth. His executives were Pepsi focused and intent on increasing market share 0.1% a time. To beat Pepsi, they want to at least increase 0.1% at a time. But Roberto decided to stop competing against Pepsi, and instead he competed against the situation of 0.1% growth. And what is that he has done? He asked his executives, what was the average fluid intake of an American per day? Fluid, general fluid. The answer was 14 ounces. And what was Coke's share of that? 2 ounces. Roberto said Coke needed a larger share of that market. The competition wasn't Pepsi. It was the water, tea, coffee, milk, and fruit juices that went into the remaining 12 ounces. And the public should reach for a Coke whenever they felt like drinking something. Whenever somebody felt thirsty, they should approach Coke more faster than the water, tea, coffee, milk, or fruit juice. So to this end, Coke put up vending machines everywhere, every street corner. And sales took a quantum jump, and Pepsi has never quite caught up since. So that is it. To sum up the story of the hare and tortoise, never give up when faced with failure. Fast and consistent will always beat slow and steady. Work to your competencies. See you tomorrow.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
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 Thank you.